Hello student, welcome to my channel that is soil and land management. Today the interesting topic here that is the salt affected soil in India. So we know that India have nearly 329 million hectares of the total geographical area. So out of that area, nearly 60% area is under the cultivable, means nearly 140 million hectares under the cultivable. And total, if you see the land degraded area in India, that is 147 million hectares land under the degradation. That is due to the water erosion, that water logging, wind erosion, salinity, alkalinity, and acidification. Due to the water erosion, there is a 94 million hectares land is under the degradation, and due to the salinity, alkalinity, acidification, nearly 23 million hectares land under the degradation. Water logging area under the India, that is 40 million hectares, and wind erosion area, that is 9 million hectares. So there are 7 million hectares area, salt affected area is there in India, that is 2.5% of the geographical area of the India. From that, 3 million hectare is the saline soil and 4 million hectare is the sodic soil. If we will see the highest salt affected area we will found in the Indo-Gangetic Plain, that is nearly 2.34 million hectare area. Out of that, 0.56 million hectare area is the saline soil and 1.787 million hectare is the sodic soil. If we will compare the states in India, 75% salt affected soil will observed in the Gujarat, Uttar Pradesh, Maharashtra, West Bengal, and Rajasthan. Here the state-wise the salt affected area in India. The highest saline soil, if you see, that is in Gujarat. Second highest in the West Bengal, and then Rajasthan and Maharashtra. The highest sodic soil we will observe in the Uttar Pradesh, followed by Gujarat. So what? How the salt affected soil will develop, and what are the factors responsible for the salt affected soil development? So we have categorized like that natural process of soil salinization and the anthropogenic process of soil salinization. So first one is the the primary process of soil salinization is called the primary salinization, and anthropogenic process of soil salinization is called secondary salinization. So in that, the first process is the weathering of parent material. So when the parent material will get weathered, so it will release the different salt, and that salt will solubilize in the water and move from one location to other location, and will cause the salinity. And in the semi region where uh, the rainfall is less and evaporation is more, so in that area the accumulation of salt will be the more. So then a fossil salt which is deposited in the marine and lacustrine area will cause the salinization, and the coastal area near to the sea, due to the ingression of sea water into the soil will increase the salt content, and also due to the salt laden winds and rains which contain the salt, which also increase the salt concentration soil. And due to the transportation of the salt from a higher slope to the lower slope, which carry the salt along with the water and cause the salinization. Then the anthropogenic factor for the soil salinization, also called the secondary salinization, that is the cleaning of the land. It will convert the perennable vegetation into the annual vegetation, which causes soil salinization due to the seepage, and change of the land use from the forest vegetation to the annual vegetation, which reduce the evapotranspiration and increase the leaching. So because of that, the groundwater quality will change, the salt concentration will increase, and maybe due to the impermeable nature of the subsurface layer which cause the seepage flow. Because of that, low lying lands will get salinized. Then a canal area, due to the seepage process, the canal area or the high water area in the canal area, mostly if you see the best example is the water logging and soil salinization in the Indira Gandhi Nahar Proyojana, where the salt affected soil will see. Then next one is the overuse of the agrochemicals like fertilizers which contain salt. which also increases soil salinization. Then use of the waste material, which add the salt content in the soil. If you use the over exploitation of the groundwater, so that groundwater will contain high salt, we also call the soil salinization. So this are comes under the secondary salinization process. Then the incorrect irrigation methods. If you use the groundwater of the bad quality, or you can say the groundwater will have the high salt content, and that water will frequently, the definitely the salt water content the soil will increase on the groundwater also will get the uh, more salt water content. Then next one, what are the types of the salt affected soil? Generally there are three types: saline soil, sodic soil, and saline sodic soil. So sodic soil also we can say the alkali soil. Here are some characteristics of the salt affected soil. The saline soil, first one is the characteristic soluble salt. Saline soil will have the high soluble salt, sodic soil will be low, and saline sodic soil will have the high sodium, high soluble salt. If you will see the EC of saline soil, that will be the more than 4 decisiemens per meter, and sodic soil EC will be less than 4, and saline soil EC will be more than 4. Then if you see the pH of saline soil will be the less than 8.5, and it is in the range of 7 to 8.5. Sodic soil pH will be more than 8.5, and saline sodic soil also the pH is more than 8.5. Then the sodium status, that is ESP of a soil, that is exchangeable sodium percentage. The exchangeable sodium percentage is less than 15 in the saline soil, and is more than 15 in sodic soil, and also more than 15 in saline sodic soil. And if you see the dominant cation, the calcium, magnesium, sodium is the dominant cation in the saline soil. So only sodium is the dominating in the sodic soil. In saline sodic soil, the dominant cation is the sodium, calcium, and magnesium. If you see the dominant anion, that is the chloride, sulfate, uh, nitrate will be present in saline soil, and in the sodic soil, the dominant anion, that is the carbonates and bicarbonates. In saline sodic soil, the carbonates, bicarbonates, chlorides, sulfates, nitrate all will be the present. The structure which is present in the saline soil, that is the granular and subgranular blocky structure, and the sodic soil, that is the prismatic or columnar structure. And in saline sodic soil, we see the moderately weak to moderate blocky and massive structure. Compaction, there is a slight and moderate compaction we'll see in saline soil. In sodic soil, we'll see the hard compaction, even also in saline sodic soil. Color of soil, the saline soil color is a light in color due to the accumulation of salt on the surface, and the color of sodic soil is the dark due to the solubilization of the humus substances in the sodic soil due to the presence of more sodium. So the soil will get a dark color. And the saline sodic soil, the color will varies presence of the which cation and anion is dominant. Then the organic matter content. So organic matter content in a saline soil is compared to normal soil is less, but it is more as compared to sodic soil. Organic matter content in sodic soil is low as compared to the saline soil, and also in saline sodic soil the organic matter content is low. Soil structure is good, and in sodic soil soil structure is poor. So the permeability and infiltration rate is good, moderately to high in saline soil, and sodic soil is very low due to the compaction and the formation crust in the sodic soil. In saline sodic soil, it depends which cation is present. In surface picture, if you see the saline soil, the white crust will be observed. When sodic soil, there is no white crust. Maybe the cracks we will see due to the presence of sodium. Plant growth, if you see, the plant mostly affected due to the osmotic effect of the salt. In sodic soil, the plant is affected due to the poor soil structure, waterlogging condition, runoff, and high pH. If you see the nutrients availability in the saline soil, the most of the nutrient will be available. In sodic soil, nutrient availability is poor. So where these soils will occur, mostly the arid and semi-arid region, the saline soil will occur. In a rainfed region, sodic soil will occur where the poor drainage condition will be there. So these are some characteristics of this salt affected soil. So, but if you see the best criteria to recognize the saline soil or to characterize the saline soil, that is the saline soil is EC, and for the sodic soil is ASR, SAR, and ESP. The ESP is more than 50 means sodic soil, or SCR, that is the another criteria, that is the sodium adsorption ratio. If the more than 13, soil is the sodic soil. Then how salt affected soil form? In that first one is saline soil. What are the factor responsible for the formation of sodic soil? Sorry, saline soil. The saline soil, the process will form that is called salinization, and mostly found in the arid and semi-arid region where the rainfall is less than 500 mm. Under a humid condition, also it will found only in the river bed area or the low lying area. In the saline soil form is arid and semi-arid region due to the low rainfall and high evaporation rate. If the drainage is restricted, so the high groundwater table will be there. So that high groundwater table, because of high groundwater table, the water will get evaporated and salt will accumulate on the soil surface. Another factor is the low soil permeability. If the soil permeability is low, the water will move up to the sub distance, and again it will come onto the surface due to the evaporation process. So the texture, another factor responsible for factor for the saline soil, that is the high texture soil will not allow the water to permeate. So the salt will accumulate in the soil, and the presence of different indurated layers like clay pan will be there, caliche layer will be there. Caliche layer will form due to the presence of high silica. So most important factor for the development of salt affected soil is the low rainfall. If the rainfall is high, the leaching will occur, leaching of salt will occur. But in arid and semi-arid area, the low rainfall will occur and evaporation rate will be the high. So because we know that the water carries the salt, and the water will get evaporated once. The salt will accumulate on the soil surface. And the important factor, that is the soil condition, another important factor. If the soil is not permeable to the water, or soil is not have the good drainage capacity, so then salt will accumulate in the soil. And third one is the groundwater table. If the groundwater table is near to the surface, the water will get due to the capillary action, it will come into the surface level, and that water will get evaporated and salt will accumulate on the soil surface. In the saline sodic soil, how it will form? In saline sodic soil, the major cation will play the role, that is the formation of saline sodic soil is sodium. If the sodium concentration is more than saline sodic soil, then the soil will turn into saline soil will convert into sodic soil. So from my point of view, the saline soil will convert into sodic soil due to the increase in the concentration of sodium as compared to saline sodic soil. So that sodic concentration will measure in milliequivalent per 100 gram of soil. In arid region, when the soil solution become concentrated due to the evaporation and the absorption of the water by the plant, so the solubility limit exceed. So then the calcium will convert into calcium sulfate and calcium carbonate or magnesium carbonate. Then the sodium concentration will increase. When the sodium concentration will increase, the saline soil is converted to sodic soil. So another factor I will feel, that is the vegetation. With the vegetation will increase due to increase the slight rainfall, because I know that the sodic soil mostly found in the Indo-Gangetic plain where the higher irrigation water will be available. So if we increase the irrigation water, it will increase the biomass. If we increase the biomass, the organic carbon content will increase. Because of increase the organic carbon content in the soil, the CO2 concentration will increase. That CO2 will convert into carbonates and bicarbonates, and that carbonates and bicarbonates will react with the calcium and magnesium, and calcium magnesium will convert into the calcium carbonate or calcium bicarbonate, or magnesium carbonate into the magnesium bicarbonate. So only one element is dominant in that country, that is sodium. So the vegetation also plays a major important role for the, and during decomposition the CO2 will release. So that's why the saline soil is converted to sodic soil. The another soil that is formed due to the saline, that is another soil that is saline and alkali soil that formed due to the both combined process salinization and alkalinization. That is formed due to the leaching. When we will do the more leaching, the Na will convert to NaOH, so pH will increase. So, what are the criteria we'll use to characterize the saline soil? One is the salt concentration. If the salt concentration is very high, we will say the soil is a saline soil. Another criteria that is the osmotic pressure, that is OP. If the very high OP of the soil is very high, then the soil is saline soil. The effect of saline soil is the wilting and nutrient deficiencies. If the salt concentration is more than 0.1%, then it will affect the root growth. Another criteria is OP. OP is calculated by the formula OP is equal to 12.06. The depression of T, that is the temperature freezing point depression, minus 0.21 depression of freezing point to the power. Then OP and EC have the one relation. OP, if you want to calculate, we have to calculate for EC. So EC into minus 0.36, you will get OP. Okay, so OP is also another criteria we will use to characterize the saline soil. Then another criteria is the EC of the soil saturated extract. If the EC used for assessment of the soil, saline soil, if the EC less than 2 decimal per meter, the soil salinity mostly negligible. And if the 2 to 4, the yield of this very sensitive crop is restricted. If the EC 4 to 8 decimal per meter, the yield of the many crop is restricted. If the EC is 8 to 16, only tolerant crop yield is only tolerant crop will give the satisfactory yield. If the EC is more than 16, only few tolerant crop will give the satisfactory yield. Then another criteria used to check the characterize the saline soil, that is the concentration of the water soluble boron. So if the critical limit of boron for the safe plant growth, if the boron is less than 0.7 ppm, the crop can grow well. If the 0.7 to 1.5 ppm, the crop will affect. If the 1.1, if the boron concentration is 1.5 ppm or more, then the soil is unsafe. Then alkali soil. How to characterize? What are the appraisal we'll use to measure the characterize alkali soil? First one is the exchangeable sodium. If the exchangeable sodium is more than 15%, then the soil is alkali soil. Another criteria is pH. If the pH is more than 8.5, so that is the sodic soil. And the third criteria that will is that is SAR, sodium adsorption ratio, which is given by the US Salinity Laboratory. The major contribution is by the Richard. So SAR formula is the sodium divided by the under root of calcium plus magnesium by 2. So these are the three parameters our appraisal will use to uh, characterize the sodic soil. This is the relation between ESP and SAR relation. If the SAR is more than 13, then the soil is the sodic soil. Then what are the problem we will face by the saline soil? The problem that we face the saline soil, that is the wilting of the plant. The soil is become barren, but it's a productive. The major problem will come in the saline soil, that is the nutrient uptake, because the water uptake in saline soil will get reduced because of increase in the osmotic potential, and because of increase in the osmotic potential, exoosmosis process will occur. So soil will hold the water so tightly, so plant cannot uptake that water, and also the permanent wilting point of the soil also will get increased, so the water availability will in the saline soil will get reduced. In sodic soil, if you see, due to the sodium concentration, the physical and chemical properties will change. Physical property in the sense the dispersion of soil particles will occur, that's called the defoliation, and so that the crusting will form, and the infiltration will decrease, permeability of the soil will reduce. So the in the last, there is a loss of the soil structure and development of soil crust and compact soil. So other physical properties that will get disturbed, that is the hydraulic conductivity, drainage will reduce, microbial activity also will get reduced. Then what is the effect of the saline sodium soil? That is specific ion effect we can say. That is the sodium is dominating, so the deficiency of calcium, magnesium we will see. And pH will increase in the formation of carbonates and bicarbonates will have the negative impact on the plant roots and development. Then effect of soil salinity and soil condition. If you see the what are the general effects will be there due to the soil salinity and the solidity. One is the on soil structure because of the increase in the sodium concentration. The dispersion will occur because of that poor aggregation, crusting, and hardening of soil will be there. So the stability will reduce, the erosion will occur, then the porosity of the soil will reduce, infiltration rate will reduce, so drainage of the soil will less, so the salt accumulation is increase more, and the root in penetration in the soil also get reduced. Then the soil aeration will get reduced, so oxygen content will reduce, so the root respiration will get affected. Then also the water ability, because increase the salt concentration, osmotic potential will get increased. So if the water is present also, the plant will not uptake that water. Then the pH. The pH is more than 8.5, nutrient imbalance will occur. So plant nutrient will not be available. If you see the microbial activity, so microbial activity get reduced due to the high salt concentration, and the organic matter decomposition and the nutrient cycling will get disturbed. Then osmotic trace we will see if the plant will uptake the water with the high salt content. The osmotic trace we will see in the plant roots on the leaves. So also the plant will face the drought-like symptoms like wilting and slow growth. And because of the excess salt content, like the sodium and chloride content will be there excess, so it will show the toxic symptoms on the plant. So that we will see the leaf burning, chlorosis, and necrosis symptoms. So these are some general effect. So also the germination rate will get reduced, so because of the high salt concentration, seed germination will get reduced, seedling emergence will not occur, so establishment also will not occur. So photosynthesis rate will reduce due to chlorophyll content will get reduced, so the photosynthesis will affected, and so stomata opening closing also will get affected. So indirectly we'll say the increase in the salt content in the soil, the photosynthesis rate will get reduced. Then growth and yield get reduced due to the less uptake of water and nutrient. So if you want to manage that soil, so how we will go to manage that soil? So what criteria we have to select before the management and before the reclamation of that soil? We will think about the saline soil. The what criteria we will have to think. So first one is the quality of irrigation water. So what is the quality of that irrigation water? Is it good, or only we are using the bad quality water for the irrigation? Then what is the salt concentration in the root zones? How much salt is distributed? How much area? How much depth? And how much the concentration of the salt? Then the level of the subsoil water. What is the groundwater level? The high groundwater level means we have to go for the drainage practices. Then what is the drainage condition of the soil? What is the permeability of the soil? So this factor we have to consider before the reclamation. And what technical requirement we should do for the saline soil? First one is the drainage. Soil should have the good drainage, because if we give the water, again stagnation problem will be there, and after the evaporation salt content will get increased. Then we should have the sufficient water, that is good quality of water. That water should have the low ec, low sar, low tss. Okay, so because if we have the sufficient good quality of water, then only we can meet the demand of the crop and reduce the salt content below the root zone. Then we have to make the land level. We have to create the bunds for stagnation of water and follow the some agronomical practices, so the leaching requirement will increase, and efficiency of uh, decrease of the salt content in the soil will get improved. Then most important thing is the quality of the irrigation water. So these are some technical things we have to consider before the reclamation or management of the saline soil. So what method we are going to follow for the management of saline soil? First one we will focus, that is the eradication. How to we can eradicate? So most common method we use to reduce the excess salt concentration in the saline soil, that is the drainage, and second one the leaching is also called washing also, flushing also. So if the combination of this method, like the flooding after the tile drainage, it will be most effective, because leaching method is effective only when the drainage condition is good, otherwise it is not good. So what is meant by the leaching requirement? If you are going for the leaching requirement or reducing the salt concentration, we have to go for the leaching option. What is leaching requirement? So leaching requirement is the fraction of the irrigation water that must be leached through the root zone to control the soil salinity to the specific level. So if you see in terms of mathematical equations, the leaching requirement is the ratio of the depth of the drainage water to the depth of the irrigation water. Okay, but some condition we have to also assume, that is the uniform area application of irrigation water. No rainfall should be there. No removal of salt in the harvested crop. Then no precipitation of soluble salt, and the ratio is equal to the inverse ratio of the EC of the soil, EC of the water. So this factor we have to consider. If because if you are giving the water and when you are calculating the leaching requirement, means how much water we have to give to reduce salt concentration, we should consider these things. Otherwise, we will calculate the wrong leaching requirement, wrong amount of water required. This is the formula: depth of the drainage water divided by depth of the irrigation water in 100 is equal to irrigation EC of the irrigation water divided by EC of the drainage water into 100. So this is the formula we'll use. Then another method we will go, that is the conversion. Conversion means we use of the different chemical amendment to convert the sodium into the another soluble form. So those amendments are the gypsum will use, sulfur we will use, then limestone will use, but the condition will change. When to use sulfur, gypsum, when the saline and alkali soil is there, the pH is up to 9, then go for gypsum. The sulfur, iron sulfate or iron pyrite is there, then use when the soil pH is between 8 to 9. Go for the limestone if the soil pH is less than 8. Okay, then you will apply the gypsum to reduce the sodium concentration in the sodic soil. So what kind of reaction will get, what kind of reaction will occur? And so when we will add the gypsum will react with the sodium carbonate and then form the calcium carbonate and sodium sulfate, which is soluble in water, will get leach out. So what on the place sodium is there when you are adding the gypsum. So calcium is represents the sodium. Sodium sulfate form, it will get leach out. When you will add the sulfur, sulfur will get oxidized, form the H2SO4. That H2SO4 will react with the sodium carbonate, will form the sodium sulfate. The sodium will get leach out. When you use the iron sulfate, so iron sulfate will get oxidized, will form the iron sulfate will get oxidized, form the iron sulfate. Iron sulfate convert into H2SO4. That H2SO4 will react with the carbonate, calcium carbonate. Okay, the calcium sulfate will form. Then calcium sulfate will react with the sodic soil. The sodium will exchange and form the sodium sulfate and get leach out. So like that way we are reducing the sodium content in the soil. So most important is first one is the amendment followed by the leaching requirement. So how we can control the salt accumulation in the soil, that is also important, because we have to also focus on how to reduce the salt concentration and how to remove the salt concentration. So in control method we will go for this, how to reduce the increase of the salt concentration in the soil. So the retardation of evaporation is important process. This will save the moisture and also the retard upward movement of the soluble salt in the root zone. So use of the salt free irrigation water you should use for the irrigation purpose. And in such condition where the salt saline soil is more, sodic soil is more, and the water, good quality water is less, then choose the salt resistance crop. So highly salt resistant crop like barley, sugarcane, cotton you can use. Moderately salt resistant crop, wheat, rice, maize you can go. And low salinity crop like wheat, radish, and legume crop, you should not use those crop in a saline and sodic soil. Then what is mean by leaching requirement? So leaching requirement main principle is the replacement of the sodium by the other cation like calcium. So all calcium compound we can use for the reduction of the sodium content from the soil, or the amendment for the sodic soil, but gypsum, which is the best and cheapest because it will solubilize fastly. The definition of gypsum requirement is the calculation of the amount of gypsum required to reclaim the sodic soil. So, how to calculate dosage of gypsum requirement to reclaim the sodic soil? It have the also the good advantage. So, sodic soil we will apply the gypsum to reduce the ESP of the soil up to the 10. Less than 10 up to the 10 ESP of the soil is good for the physical condition. Okay, so what are the ESP there? More than 10. So we have to get reduced less than 10. So for that, how much gypsum we are applying, that one we have to calculate. The gypsum requirement we will calculate by the NADM method, Schoonover method. The gypsum required formula is ESP initial minus ESP final into cation action capacity divided by 100. So that will calculate the milli equivalent of calcium per 100 gram of soil. Okay, ESP is the initial ESP before the reclamation, and final ESP that will keep constant 10. Okay, see the cation action capacity. Suppose we have to calculate the gypsum requirement, the ESP of the initial ESP 60 and final ESP 10, and cation action capacity is 30. Then how much the gypsum requirement? So 60 minus 10 into 30 divided by 100, it will be the 50 milli equivalent calcium per 100 gram of soil. Since the 1 hectare soil up to the 15 centimeter depth, the weight of that soil is the 2 into 10 to the 6 kg. So 1 milli equivalent gypsum is equal to 860 ppm. So theoretically, we see 860 into 2.26 into 15 divided by 10 to the power 6. So we will get 20.80 tons. That much gypsum we have to add per hectare. So also we have to consider some points before applying the laboratory calculate gypsum. That is the purity of the gypsum and moisture content. Purity is very important. So what are the gypsum requirement calculating the laboratory? We have to multiply into the 1.25 factors. So that factor we will consider for the purity, soil factors, and environmental factor, moisture contents. So 1.25 is the gypsum factor. We will multiply into the laboratory gypsum requirement to get the uh, field gypsum requirement. Okay. So other than gypsum also we can go for the other compounds. So what is the equivalent for the gypsum? That compound we will see. If we use the gypsum 1 ton, so how much sulfuric acid we can use as compared to gypsum? That will be 0.5 tons. If you use the sulfur, then you can use the, if you are using the gypsum 1 ton, so if you can use the sulfur only 0.18 tons. If you go for the iron sulfate, you have to use 1.62 tons, but the gypsum we have to use 1 ton. So like that is the comparison also there between the other compound with the gypsum. So what are the factor we have to consider the for the gypsum required? That is efficiency factor. Efficiency of gypsum is depends on the fineness and purity. Okay, and what are the limitation we will face for the application of the gypsum requirement? That is the soil texture, surface area, types of clay, organic matter how much, and how much exchangeable magnesium is there. Okay, so we'll see the reclamation of saline soil. In that reclamation soil, we have seen the leaching requirement, that is washing of the soil with the good quality of irrigation water, washing of soil below the root zone. Then for that we have made the one assumption that the drainage should be the good surface or subsurface drainage should be there to remove this saline water, and the land leveling should be there for the uniform distribution of water or stagnation of water. Then irrigation management use only the good quality of water. Then follow the mulching to reduce the evaporation to minimize the salt concentration in the soil, or go for the salt affected soil. Then we have done the reclamation of sodic soil by application of gypsum and other uh, calcium containing or sulfur containing compounds. Another method also we can use for sodic soil, the addition of organic matter, the deep flowing tillage to improve the infiltration and select the alkali tolerant crops. Why to add the FIM or organic matter? Because it improves the structure organic microbial activities, and also it release the acid. That acid will solubilize the sodium or sodium carbonate, so the sodium content will get reduced and soil structure also will get improved. If soil structure will get improved, the water infiltration and the percolation will increase, so that the water the sodium is there we can remove fastly, so the efficiency of reclaimed sodium oxide will get increased. Okay, so some physical method we'll consider for the saline soil management, that is the land leveling, deep flowing. Deep flowing means the breaking up the subsurface hard pan. Land leveling means the we have to level the land for the uniform distribution of water. Mulching, that is used for the evaporation, reduce the evaporation and prevent the upward movement of water. And soil profile modification. Soil profile modification means we have to change the texture of the soil by adding the salt, so that the infiltration and permeability of soil will get increased. Then hydrological method we have seen in that the leaching. So do the leaching with good quality of water. Then the drainage, surface and subsurface drainage. Then irrigation management with proper scheduling with good quality of irrigation of water. Then chemical method we have seen the application of gypsum, sulfuric acid, iron sulfate. Biological method we can go for the green manuring, which will improve soil structure, add organic matter, which release the acid that will solubilize the sodium carbonates and reduce the sodium content in the soil. Go with the salt tolerant crops like rice, barley, cotton, and most important is the agroforestry. So agroforestry is helpful for reducing the high water groundwater table and improve the soil, and it also acts as the natural drainage channels. So this is the about the total about the how the salt affected soil will form. What are the processes responsible for soil affected soil formation? How to characterize the salt affected soil? How much it is distributed in India, and how to manage the soils. So thank you. Please like and subscribe my channel.